Welcome back, Business Calculus students. In this second video of our final review worksheet series, I'm going to be working problems 5 through 10, simply reviewing rules of differentiation. So let's jump right in. Problem 5, we're to use rules of differentiation to find the derivative of the function and then simplify as far as possible. So on problem 5, we're dealing with several distinct terms. Each term has some power of x. Notice that last term, though, is expressed as a fraction. In order to apply the power rule to that particular term, it will be easier to deal with it if it's in the form of x raised to a power. So notice I'm not differentiating. This is still y. I'm just rewriting this in a form that will be easier to differentiate. So we'll rewrite that as x to the negative 2. Now we're ready to find the derivative. You can call your derivative y prime. You can call it dy over dx. It doesn't matter to me. So let's apply term-by-term differentiation using the power rule. On the first term, recall if we have a constant multiplier, we filter that through to the derivative. Then we're going to differentiate x squared. We bring the power down in front, keep the base the same, and decrease the exponent by 1. On the second term, we have x raised to the power of 1. Hopefully you're used to differentiating and you know that derivative is 1, but let me remind you why that's true. The exponent here is 1, so I'm going to bring the power down in front, keep the base the same, and decrease the exponent by 1. So there it is. X to the 0th power is always equal to 1. On the third term, we have constant multiplier negative 3, and we apply the power rule to x to the negative 4 by bringing the power down in front, keeping the base the same, and decreasing the exponent by 1. Got to focus when you're dealing with those negative exponents. Negative 4 minus 1 is negative 5. Then finally, for our last term, we're going to bring the power down in front. Base stays the same. Decrease the exponent by 1 to get negative 3. So we've successfully differentiated. Now we just need to simplify. So the first term becomes 4x. Second term, now don't think that's 0. Remember, anything to the 0th power is equal to 1. On the third term, we have negative 3 times negative 4, which is positive 12, x to the negative 5th. And our last term, we'll just clean it up and write it negative 2x to the negative 3. Now, in general, you want to express your derivative using the same type of notation as your original function. However, the original function mixes both negative exponents and fraction form. So you could leave these two terms as they are, or you could express them in fraction form. Either way is going to be fine. So our derivative is 4x plus 1 plus 12x to the negative 5th minus 2x to the negative 3rd. Or if you prefer, we can call that 4x plus 1 plus 12 over x to the 5th minus 2 over x cubed. Full credit either way. But do notice on those last two terms, those negative exponents only govern the x, not those coefficients. So the 12 and the 2 stay in the numerator while the power of x goes to the denominator. All right, so that's our simple power rule executed term by term. Awesome, we are on page 2 of our review, making progress. Problem 6, we are to find the first derivative. In this case, notice I'm dealing with the product of two functions of x, so I'm going to apply the product rule. So for my first derivative, if you'll remember the pattern, we keep the first factor the same, and then we multiply by the derivative of the second, plus derivative of the first function times the second one as is. So that's our plan. That's the map of our product rule. Let's go back and execute those derivatives. So the first one, of course, is x minus 3. The derivative of 4x squared plus 7, term by term. Notice the derivative of 4x squared is 4 times 2x, so its derivative is 8x. And the derivative of the constant 7 is 0. So there is the derivative of the second term. Plus the derivative of x minus 3, as we saw in the previous problem, the derivative of x is 1. And again, the derivative of the constant negative 3 is 0. So that derivative is completed. And we've got this last term as is. So the calculus part is done. Now we're ready for some algebraic simplification. I'm going to break up these parentheses using the distributive property. So we have 8x squared minus, what's 3 times 8? 24x. And on this second set, you can distribute the 1, which doesn't change that second factor. And then finally, combine like terms. 8x squared plus 4x squared gives me 12x squared. Negative 24x would be next, and plus 7. Okay? Full credit that way. If you want to say y prime equals, that's good too. I'll be looking at your work. I'll be looking at your simplification. Remember, I will give you credit for successfully executing the product rule. I'll be checking the calculus. Then I will check the algebra. So even if you can at least get started on these problems, it's definitely worth something. So don't be tempted to leave anything blank. Problem 7, we're still finding the first derivative, but notice the nature of this function is different. On number 6, we have the product of two functions of x. In problem 7, we have the quotient of two functions of x. So that signals to us we should apply the quotient rule. Now, remember, practice good habits with your quotient rule. And by that, I mean begin by squaring your denominator. Remember, if you begin by squaring your denominator, that reminds you how to get the numerator started. The order of the numerator is important because there's a difference there. In the product rule, we're looking at the sum of two terms, and the order doesn't matter. But in the quotient rule, we have the difference of two terms. So that means I got to get them in the right order. So to remember that, again, square your denominator first, and then lead with that term in the numerator. Then follow the pattern, same times derivative minus derivative times same. So by that, I mean keep the denominator the same, multiply by the derivative of the numerator, minus derivative of the denominator times the numerator as is. All right, so that's our map. That's our plan for the quotient rule. Let's go back and execute those derivatives. The derivative of x squared minus 2 is what? Can you get it? 2x. And how about the derivative of 3x minus 4? Can you test yourself? Can you anticipate what it is? You should get 3 times x squared minus 2. All over. Don't leave that denominator behind. Write it down with every step so that you don't forget it. Our last step here, now notice calculus is done. You get points for executing the quotient rule. Now we need to simplify. I notice the two terms in the numerator do not have a common factor. So the best I can do here is break up those parentheses with the distributive property. So let's distribute the 2x to that first set of parentheses. We're going to get 6x squared minus 8x. And be careful here, make sure we distribute negative 3 to these two terms. That's going to give me negative 3x squared plus 6. Again, just string that denominator along. Don't be tempted to multiply it out. If you were thinking that, should I FOIL? If you did, no problem. You get credit for that. But if you leave it factored, it's better. Because if I happen to have a common factor in the numerator, I'll be able to reduce it. And I won't see that common factor unless it's in this factored form. Okay, let's combine like terms. We have two x squared terms. So 6x squared minus 3x squared gives me 3x squared. We have minus 8x and plus 6 left over. And we have denominator 3x minus 4 quantity squared. Okay, so let's express our derivative. And we are good to go. So we've looked at power rule, product rule, quotient rule. It is essential that you know those for the final. Can't really survive this class without knowing those basic differentiation rules. And by the way, pat yourself on the back. This is calculus. You are doing calculus, which is not an easy thing to do. So good job getting this far. Let's look at next the chain rule. When do I use this strange little chain rule? I use the chain rule, of course, on number 8. Why? Instead of just having x raised to a power, I have a function of x raised to a power. So I have an inside function and I have an outside function. The outside function is expressed in that exponent. So when I find the derivative, I'm going to pretend first I'm just executing the power rule. So notice we have a constant multiplier 4. We filter that through to the derivative. And then I'm going to apply the power rule. This means I'm differentiating that outside function. So I'm going to bring the exponent down in front. Now be really patient here. Keep the base the same. Don't be tempted to differentiate that base. Okay, so power comes down in front, base stays the same, and decrease the exponent by 1. That's our basic power rule. But because the base is a function of x and not just an ordinary x, the chain rule says we have to multiply by the derivative of the base. So we have 3 times 2x here, or 6x. All right, so calculus is done. Next, we just need to simplify. So the product of these constants here gives me a negative 20. I'll do this step by step so I don't lose anybody. I'm going to copy this one down. And notice I have just some basic constants here. I can multiply those together. And let's bring this little monomial term to the left. So multiplying the negative 20 and the 6x, we can complete our derivative to get negative 120x times 3x squared minus 2 to the negative 6. And that's it. Now, please don't be tempted to think, oh, I'm going to distribute the negative 120x here. That does not work because remember the order of operations says I would have to evaluate the exponent before the multiplication, and I can't evaluate that exponent. So our derivative is good to go. So you've got power rule, product rule, quotient rule, and chain rule. The next part of our practice derivatives here involve exponential and logarithmic functions. So let's refresh our memories on how to do this. Hold on, my screen's frozen. Let me fix it. Okay, we're good. Sorry for the little blip there. Problem number 9. Find the derivative. Notice we're dealing with an exponential function base e. So we're going to remember all of our ordinary rules and how to find the derivative of an e. So my first term is a constant. The derivative of a constant is 0. You can write it there. You can just omit it. I'll write it for clarity. And the next term, we have a constant multiple, 5, times we need to work on the derivative of the e. Remember, e is different than the power rule. We make a copy of the e exactly as it appears, and then, chain rule says, multiply by the derivative of the exponent. So I'm looking just at the exponent negative x squared, and I find its derivative, which would be negative 1 times 2x, and that's that. Make a copy of the e, multiply by the derivative of the exponent. So let's clean it up a bit here. Again, if you take those little terms to the left of your exponential expression, it makes it nice and readable. So I'm going to multiply negative 5 times negative 2x to get 10x, and then glue the e on the end here. Okay, now be careful how you write that. Make sure that you have this level and then you have that superscript for your exponent. So our first derivative on this one, 10x e to the negative x squared. Okay. Number 10, we have to remember how to deal with a natural logarithm. So the plan for differentiating a natural logarithm, let me remind you, we're going to take the argument, that's all this stuff in parentheses, take the argument of the natural log and put it in the denominator. And then I'm going to find the derivative of that argument and place that in the numerator. Test yourself. What's the derivative of 5x squared plus 2? I hope you got 10x. If you got 10x, you're in good shape. Notice the derivative of this log function doesn't have a logarithm. There's no natural log in the derivative. Okay, so we say the derivative of this natural log function is algebraic. So remember, no natural log in the derivative. We simply take the argument in the denominator and the derivative of that argument in the numerator. If you remember that process, it's really quite simple. All right, in the next video, we will look at applications of the derivative. Thanks for listening.